Quantum mechanics is the physical theory that describes the behavior of atomic and subatomic particles. Quantum particles behave in a way that is logically and physically different from that of all other objects. According to quantum mechanics, some properties of the particles are indeterminate until they are measured, and only after the measurement do they get specific values. In 1935, Erwin Schrödinger suggested the following thought experiment in connection with the measurement problem.
Let's take a box and put into it this device which works as shown.
When the radioactive element decays, it emits a photon, which in turn activates a mechanism that releases a poison gas.
And now? Radioactive decay is a quantum process. In a given time interval, the element can decay or not. And until we make an observation, we are in presence of a superposition of states.
The state of the photon is a superposition of emitted or not emitted. If the photon is not emitted, the cat remains alive. If the photon is emitted, the cat dies. An observation or measurement forces the system to collapse into one of the two states.
So, before opening the box, what is the state of the cat?
Am I dead? Alive?
Do you need a psychologist? Do you feel yourself observed? Well, you're not mad. It's the same for me. I do exist and I don't exist. That's what can happen to all of us quantum particles. Come along, I'll show you the quantum world.
But we are prisoners here.
To be part of a thought experiment has its advantages. Follow me.
What a strange world. It's very foggy. Everything is...
Here, everything is rather undefined. You have to get used to it. Nonetheless, this is the world of the foundations of all that is known as certain and well-defined.
Somewhat foggy foundations, aren't they?
You'll see at the Museum of Historical Experiments. You'll clear your mind up.
Is it far away?
Right at the interference peak.
Let's take all the ways together and we'll very likely arrive.
All the ways together? That is impossible.
Never mind, nobody can see us here. I'll go first, don't look at me, and then we'll make it. What now?
But I can't take one road and 3 others at the same time.
Look who's talking. One who is dead and alive at the same time. Don't you understand that it's just the same? The same way you are dead, alive, you can be on the road A and on the road B. These are superposition states. See you later, and never look at which way I take. Otherwise, I can't know where I'm going to.
Hope I see you.
Look, I told you, you're here.
Yes, I am. But don't ask me how.
Let's go in. You'll understand it in there.
But there's nothing here.
This is the thought experiments room.
But it's empty.
We have to fill it by thinking our experiments. Here we have an experiment with water waves.
The wave that passes through slit 1 interferes with the wave that passes through slit 2. The intensity of superimposed waves is not equal to the sum of the intensities of each single wave.
You saw how waves behave. Now let's see how particles behave. For example, bullets.
The distribution of bullets passing through two slits at the same time is equal to the sum of the distributions referring to each slit alone.
Waves and bullets are really different.
And how will the quantum particles behave?
The distribution of probability for electrons passing through two slits exhibits interference fringes. Electrons behave as waves. When we observe which slit they are passing through, interference fringes disappear. In that case, electrons behave as particles.
Electrons are both waves and particles.
Ah, but you could also say neither of them.
Electrons pass through both slits at the same time as we did to arrive here.
Yes, they are in a superposition of states.
To each particle is associated a wave function. From its amplitude, it is possible to obtain the probability distribution. A different amplitude is associated to each possible behavior of the particle. The sum of all these different amplitudes gives the total wave function. I.e., we have a superposition of states whose wave functions interfere with each other. The observation causes the collapse of the total wave function, or wave packet, and the emergence of a single wave function. This means that there is no way to observe a superposition of states.
Then why do they behave as bullets without superposition when I watch which slit they are passing through?
You disturb them, and by doing so, you interfere with their behavior.
But then, is it my fault?
In some way, yes it is. Because you performed a measurement, you force a superposition state to collapse into one of two states. But mostly it is the uncertainty principle's fault.
I'm going to show you another experiment. Remember that we have to think the particle as a wave as well.
Position and velocity are incompatible observables. Given one direction, the more precisely I know the position of a particle, the less precisely I know its velocity, and vice versa. In a beam of particles moving in the y direction, the velocity in the x direction is 0, and thus it is known. In the same x direction, the position is indeterminate, the probability of finding a particle being the same for every point along x. The better we know the position in the x direction, x, the worse we know the velocity in the same direction. In fact, the velocity is no longer 0. The particle has acquired an unknown velocity in the x direction.
So you see, this is why quantum particles cannot stand still without expanding everywhere. Here is an electron. Try to stop it or to localize it.
This uncertainty principle is a great restriction. Indeed, a real nuisance.
Watch this.
How did you make it?
Exploiting the uncertainty principle. It is called the tunnel effect. For us particles, there is some probability to go across a barrier. As you can see, uncertainty principle is not a restriction. On the contrary, Look closely at those two.
What happened to them?
Vanished, deleted. They were virtual particles. They shouldn't have the right to exist, but they borrowed the amount of energy they need to exist properly.
But this is cruel. They took off their loan as soon as they came out of the bank.
According to the contract, loan can be considerable, but short-term, so the greater the amount of energy you loan, the earlier you have to give it back. Here you see another uncertainty relation.
The energy of a particle is indeterminate with respect to time. The shorter the amount of time, the greater the uncertainty on the amount of energy, and vice versa. The precision with which I can determine one particle's energy depends on the time required to make the measurement. For very short times, it is possible to acquire energy or equivalently mass from the vacuum, and this allows virtual particles to exist.
In such a short life, there's no time to do anything.
Virtual particles do a lot of things. It is thanks to them that some interactions between real particles are made possible.
Without exchanging virtual photons, real particles couldn't do much. Are you starting to understand how things work here?
There are particles, which are also waves, passing at the same time through two slits.
We can say they are in a superposition of states.
Particles do not have a determinate position and velocity, and for short times, not even a determinate energy. And when I observe which slit they're passing through, they change their behavior.
It is named wave function reduction or wave function collapse. It occurs at the time of measurement.
As a consequence, about a particle nothing can be said, neither where it is nor what it's doing.
You can't say much about it, but that is really all you can say. However, we can calculate precisely the probability of finding the particle in a given state. You can't know the outcome of an observation with certainty, but you can compute exactly the probability to get a given outcome.
It's a hard life here, isn't it?
Don't think that this world is more obscure than yours.
Certainly. At my place, nothing arises from nothing, for example.
All right, let's see.
Generally, a physical system can be described by defining its state. When the state represents the maximum amount of information, it is a pure state. Otherwise, it is a mixed state. In classical mechanics, all quantities are compatible, and as a consequence, pure states determine all the properties of the system. The knowledge of a pure state, i.e. position, mass and velocity, and forces operating in the system, allows the prediction of the outcome of the measurement of all physical quantities. In quantum mechanics, not all quantities are compatible. As a consequence, a pure state does not determine all properties of the system. The knowledge of a pure state only allows the computation of the probability of the outcome of each measurement. In classical mechanics, the sum of states has no physical significance, and state superposition is a nonsense. On the other hand, in quantum mechanics, the sum of states is still a state. As a consequence, quantum systems can be in a superposition of states. In quantum mechanics, the statement that state psi is the superposition of state psi 1 and state psi 2 means that the system in state psi could share the properties that belong with certainty to state psi 1, but also properties that are certain for the state psi 2.
Thanks. You're teaching me a lot of things, and yet I don't know your name. My name is Felix.
Sorry, I'm simply a photon. I have no name.
Ah, you're a stray photon. When I was a stray cat, I had no name like you. Don't worry, I'll give you one. I'll name you Lucius.
No, Felix, it isn't that simple. We photons have all the same properties, and you can't distinguish one photon from another.
You are like bees. But if I see a bee landing on a flower, I am quite able to distinguish it from another flying away.
Yes, that's true. But we aren't like bees. To localize a bee, you can follow its trajectory, its history.
In the same way, I can follow the trajectory of a photon.
But photons have no trajectory nor history. Did you forget the uncertainty principle?
Right. The principle that forbids us to know where exactly you photons are.
And if you don't know where we exactly are, you cannot know if that photon that now is here is really the same that was there a moment ago.
Two objects are different when there exists at least one quality which belongs to one and does not belong to the other. All quantum objects of a kind have the same properties, therefore they are identical, indistinct. Position can localize objects as bees. But position cannot localize quantum objects because of particle spread.
Therefore, if two of you swap places, I can't notice.
And this is valid for all the particles of a kind, also for electrons. Why don't we go with them, Felix? I think you'll find it very, very interesting. We'll meet again every time you encounter a photon.
Bye. See you.
Occupied.
I would like to come with you, but as I see, there's no more room.
But here is a lot of room.
I thought so, but you sent away that electron before, even though it was very small.
So what? You're not an electron. Come on, get on.
I am a cat. You aren't a racist by any chance?
Racism is not the question, but state.
Do you mean social status?
I mean that it is forbidden that two electrons occupy exactly the same state. Because of the Pauli's exclusion principle. This is the law.
Indeed, you are in the same state.
Are you crazy? Don't say that, even if it is for a joke. Can't you see I'm up and he is down? We're really different and therefore we are not in the same state.
The photon told me that you are all the same.
A photon? But for a photon it's quite a different matter. How could he know it? They are bosons. They are not subject to exclusion.
You are not bosons.
We are fermions.
Two classic particles have four possible behaviors. Both particles are in a state. Both particles are not in that state. Particle A is in a state and particle B is not in that state. Particle B is in a state and particle A is not in that state.
Two quantum particles of the same type, being identical and as a consequence being indistinguishable, have a maximum of three possible behaviors. Both particles are in a state. Both particles are not in that state. One particle is in a state, the other one is not in that state. Particles of this type are called bosons, and they have integer value of the spin. Photons are bosons. Particles with half-integer value are fermions. For fermions, the Pauli exclusion principle holds, namely two fermions of the same type having the same spin cannot occupy the same state. As a consequence, two fermions of a type have a single possible behavior. One particle is in a state, and the other one is not in that state. Electrons are fermions. An effect of the exclusion principle is the variety of the periodic system of elements. In fact, in the atoms, electrons have to place themselves in different levels, originating different elements. Furthermore, the stability of matter is the result of the exclusion principle. For example, two hydrogen atoms are distant in order to avoid that their outermost electrons share exactly the same state. Bosons have a higher probability of sharing the same state rather than of being in different states. Fermions and bosons behave in a different way because they have different values of spin. There is a spin statistics connection. In a boson system, in the minimum energy state, each particle is in its minimum energy state. In a fermion system, in the minimum energy state, the particles are not in their minimum energy state. The minimum energy of a fermion system is enormously greater than the minimum energy of a boson system. In superconductors, coupled electrons have entire spin and behave as bosons.
You know, it's up to us fermions if a structure of matter exists.
Tell me, where are we going?
To the tribunal. There is an important trial in the entanglement mystery. It seems that the locality law has been violated. They are investigating because there is a charge with incompleteness. All the newspapers are talking about this. Two particles in an entangled relation. A business of not declared properties.
Stuff for the rich.
On the contrary, we particles are rather poor. Objectively, we have few properties.
Physical properties correspond to determinate values of physical qualities. If, without disturbing the system, we predict with certainty the outcome of the measurement of a quantity, then the system objectively has that property. Quantum systems have few objective properties, i.e., not every quantity has certainly predictable values. Actually, quantum system always has at least one objective property. It is always possible to set the system in a situation so that at least one quantity is in a definite state.
Silence in court. I will now call upon the prosecutor.
Ladies and gentlemen, let me introduce the facts. We have two electrons, originated by one source. They are in a state that is the superimposition of two states. In each of those, the two electrons are with opposite spin.
The defense makes no objection.
In a more-particle system, if each particle is in a definite state, the state of the compound system is the product of the states of single particles. It is a factorized state. The factorized state of two particles means one particle in a definite state and another particle also in a definite state. Generally, in a compound system which is in a definite state, each particle is not in a definite state. In this case, the state of the compound system can't be equal to the product of the particle states. These particles are entangled. In a system compound of entangled particles, the state is given by the sum of the products of the particle states. The state of the compound system is a superposition of states correlating each other. In this case, electrons are entangled. They don't have a definite property of spin, but if one electron spins down, the other one spins up, and vice versa.
This theory of defense asserts that neither of two electrons has definite properties. I'll prove that this theory is incomplete.
One of the two electrons approached the bar.
Where is your confederate?
I have no idea, but very far at present.
Let me ask you, what is your state of spin for a given direction?
At present it's absolutely impossible for me to answer. I can only say that 50% is up and 50% down.
Do you perhaps mean that you don't have a definite spin for any direction?
Precisely. I do not have an objective property of spin.
And what can you tell me about your confederate? Do you know his state of spin?
As far as I know, he is in the same superimposed state as me.
So even they don't have any definite property of spin?
Definitely. At least till you don't perform a measurement on me or on him.
Now this seems familiar to me.
The measurement on one of the two entangled electrons makes the state of both collapse, and instantaneously the electrons acquire a definite property of spin.
I ask the court permission to perform a measurement of the witness.
Permission granted.
We obtained the result spin up for this electron. But we know now even the spin of the escaped electron.
I have no objection.
You'll agree that, whether we predict for a certainty the result of a measure of quality, without disturbing the system, then the system objectively has that property. And that is really just what has happened. We know for certainty the spin of the distant electron, and we didn't disturb it.
We agree with you.
So it is right to say that your companion has an objective property.
That is right.
Therefore, he had to have it even before I had performed my measure. You lied.
I didn't lie. He didn't have it before. Help us to understand the point you wish to make.
If the witness is telling the truth, and so the electron didn't have any objective property before the measurement, then I must deduce that it was the measurement that I performed hereby to trigger a very far electron to exhibit this property. Therefore, locality law would be violated. But I think this is impossible. In my opinion, electron doesn't tell us the whole truth. The theory is incomplete.
Objection! My client doesn't lie. The theory is complete.
I have to reflect upon this. Court is adjourned.
What is locality?
It is the principle that an action cannot have effect in a far place instantaneously.
It is clear. But the judge is coming back.
Having seen the documents, the court holds that the electron didn't lie. The theory is complete. Each electron can have no property. In fact, it is the compound system of two electrons that, as a whole, has some properties.
Two entangled systems have to be considered parts of a single system that, as a whole, has some definite properties. On the contrary, such properties remain indefinite for the component systems.
The observation causes the emergence of two single systems, and they have some definite properties.
We won the case.
This is not a simple issue. You won the case, but actually your theory violates the law of locality. Anyway, we cannot hold such a violation as a crime against the law of relativity because, according to that law, even in the case of non-local correlations, it is impossible to send any signal or information faster than the speed of light.
After the spin measurement of one of the two electrons, both states of the entangled electrons collapse simultaneously. But the principle of relativity is not violated because information is not exchanged faster than the speed of light. In order to know the spin state, observer B must perform a spin measurement, or must wait for information from observer A, which will arrive over time, not instantaneously.
Your Honor, I would like to clarify another entanglement case.
There are others accused?
I would call as witness of measurement process Felix the cat.
Objection! A cat is a macroscopic object. It isn't subject to the quantum law.
It is precisely that which has to be determinate. After all, Even a cat is made by electrons and protons. Mr. Judge, why the same law which are valid for electrons shouldn't be valid for a cat? Moreover, this cat is entangled with a photon.
Objection denied. The witness to approach the bench.
Believe me, I had no idea to be entangled. I was thinking simply to be a cat.
Don't worry, Mr. Felix. Everything is entangled. It's enough that two particles interacted with each other once in the past to make them entangled. All particles, sooner or later, interact with each other. In a certain sense, the word is not separable. Counsel, you can examine the witness.
Have you ever met this photon?
Photons are all the same. I can't know.
Indeed, this photon has a very close relation with you.
We are really entangled. We are in a state which is a superposition of two states. One in where I am emitted and the cat is dead. One in where I am not emitted and the cat is alive.
The state of the photon is a superposition of emitted or not emitted. If the photon is not emitted, the cat remains alive. If the photon is emitted, the cat dies.
So we can say that the state of the cat magnifies the state of the photon to a macroscopic degree, and the state of the photon could be even in a superimposed state.
Certainly, a photon is a quantum, but measurement determines the reduction of the wave packet, and the observer watches the photon by means of the cat either in one state or the other.
An observation or measurement forces the system to collapse into one of the two states.
But till the box is closed, that is before the measurement, the reduction hasn't yet happened, and so even the cat can be in the superposition dead alive.
I think there is no problem since we'll never see it.
No problem. Cats can't be dead alive, even if we can't see them. There is a manifest violation of the rules. Let's continue.
Nothing, it seems, prohibits the cat from being in a superposition of states.
The cat, being conscious, observes himself initiating the reduction of the wave packet even when the box is closed.
So, Mr. Cat, are you an amplifier, that is, an index indicator, or are you an observer? And if you are an observer, why are you going around with that corpse?
Mr. Judge, believe me when I say I'm innocent.
The witness doesn't answer the question. He can't answer. Then can the ampoule or the detector that clearly are not observers be in a superposition of state? Where does the reduction of wave packet happen?
In which link of the measurement chain does the reduction happen? In the first, it hasn't happened yet for sure, because the photon is in a superimposed state. In the last, it has already happened. In fact, the superposition of states can never be observed. The reduction of wave packets happens between these extremes.
What counts is that when the observer observes, indeed, the reduction has already happened.
The observer himself could be in a superposition of states. Theoretically, there is no law that forbids it.
Couldn't be possible to measure in that case. Therefore, we wouldn't have any outcome. There is no property.
This is really why we need a rule of demarcation between microscopic and macroscopic, Mr. Judge. Or the law is equal for everybody. Or, whether or not, we must know when we have to apply it and when not.
Law mustn't be equal for everybody, but actually that rule isn't discovered at present. Nevertheless, it is not decorous that the cat goes around in such superimposed state. We consequently sentence the cat to be dead or alive. We can't accept intermediate solution. It is absolutely necessary that reduction, and this works even for the ampule. The sitting is adjourned indeterminately.
Well, I suppose I could be content to be a little alive and a little dead, whereas I really would be merely alive.
Don't worry, Felix. They haven't opened the box yet. I'll wait before existing. Nothing can force me to do one thing rather than the other. If anything, I have to do both. And then, between friends...
So bye, and thanks for everything.